So in this part of this section, we're going to start converting from rectangular to polar equations. Now we can go both ways, so we're going to go rectangular to polar first, and then we're going to go from polar to rectangular. So here's the deal. If we're going from a rectangular equation to a polar equation, for instance, like this one, we're going to use those same identities that we established in the last um, video. Namely this, that whenever we want to have an x, we can replace it with an r cosine theta. Whenever we have an r cosine theta, we could replace it with an x. Same thing with r sine theta and y. You can go back and forth between y and r times sine theta. Tangent theta is y over x, and x squared plus y squared is the same thing as r squared. So the thing we have to look out for on these conversions is when to use this one, when to use this one, when it's advantageous to use tangent, when it's advantageous to use the Pythagorean theorem identity. So it's basically figuring out which things are advantageous and in which scenarios things are advantages to use and which scenarios they're not. So like in this example, x squared plus y squared equals 25. So what we're going to do is we're going to take that equation, whoops, x squared plus y squared equals 25, and say, well, which scenario replacement wise is it best to use? Or that's probably a poor way of putting it, but which thing should I be replacing with? If I start replacing the x with r cosine theta and the y with an r sine theta, you could do that in this example, but it's easier to take this x squared plus y squared as a unit and replace that with an r squared. So take the r squared, I want to have polar, so I want r's and thetas, equals 25. And then usually in polar form, we solve it for r if we can. So we can say r equals 5 by square rooting both sides if we like. Now, sometimes you say, oh, we got the positive 5, but not the negative. That's not a big deal because we can use various tricks with the theta. Remember, we can always add pi to our thetas. So if you were thinking of a point with a negative r value, we could add pi to the angle theta, and that would be the same point with a positive r value. So r equals 5 is the easiest way to rewrite x squared plus y squared equals 25. Okay? And by the way, we should know that that is a circle of radius 5, right? Hopefully we've all established that. If you graph this in terms of rectangular values, x squared plus y squared equals 25, you get this equation on the rectangular coordinate system. If you change that to the polar coordinate system, you just get a circle. It's the same circle, obviously. Either way, circle of radius 5, but this is in complete alignment with the polar coordinate system in that we do have a r equals 5. So r equals 5, r equals various values are sort of the grid lines themselves, whereas obviously circles do not comprise the grid lines in the rectangular coordinate system. So there you go. Now I want you to do some replacing, maybe some substitution to try to find the polar equation for the following rectangular equation. Do substitution, replacing, all that kind of stuff. Try to solve for r if you can and see that you get the thing. This is a linear equation, y equals 3x minus 2. So go ahead, push pause on the video, try to come up with the polar equation of this line. Right, so once you type this in, or once you start doing this, y equals 3x minus 2, there's really no other way other than just to replace the x with an r cosine theta and replace the y with an r sine theta. Once you do that, you're going to get r sine theta is equal to 3 times r cosine theta minus 2. And normally we solve this equation for r, so we'd subtract 3r cosine theta from both sides. Whoops, again, a negative 2 there. So we'd end up with r sine theta minus 3r cosine theta is equal to negative 2. And then if we're solving for r, we'd factor out an r. So r times the quantity sine minus 3 cosine theta equals negative 2. And then if I'm solving for r, I have to just divide this sine theta minus 3 cosine theta, divide both sides by that. So you'd end up with r equals negative 2 sine theta minus 3 cosine theta. And so that would be the way to to graph this linear equation in terms of polar coordinates. You can punch this into a calculator like Desmos here, and you get negative 2 over sine theta minus 3 cosine theta. You can see that you get the straight line where the slope is 3 and it intersects the graph at what we would have called in rectangular version point 0, negative 2. Obviously, that's not the same thing in the polar version, but you can see that. Now, this goes to show you, these last two examples, that there are some equations that are much easier to write in rectangular coordinates, and there are some equations that are much easier to write in polar form. So in our previous example, we had x squared plus y squared equals 25. That was much easier to write and deal with in polar form. R equals 5 is a much, much simpler equation to deal with. This one, it's probably much simpler usually to deal with this y equals 3x minus 2 in most cases. So there are some advantages to using polar, and there's some advantages to using rectangular in whatever situations we're dealing with. Now I want you to try one more. I want you to convert this rectangular equation to a polar equation. X squared equals 16y. Go ahead and push pause on the video and do that. All right, so the first thing we see, x squared equals 16y. I'm going to simply replace the x with an r cosine theta, replace the y with an r sine theta. So we end up with r cosine squared equals 16 times r sine. Well, in order to solve for r, first thing I want to do is expand this square. So r squared cosine squared on the left, 16 r sine theta. I would divide both sides by r. Notice that's going to cancel one of the r's on the left, and that's going to get rid of the r on the right. So you're going to end up with r to the first times cosine squared equals 16 sine. And then you can simply divide both sides by cosine squared of theta. So you end up with r equals 16 sine theta cosine over cosine squared theta. And if you want, you can use a calculator, to graph that and see, in fact, that you do get the same parabola that you would have gotten using rectangular coordinates. All right. So that's the idea. Okay. All right. Now, in the next examples, we're going to go the other way. We're going to start with polar equations and move on to rectangular equations. And so let's start with the basis of the graphing system, meaning r equals a number and theta equals a number. So let's think through what this means. We kind of already know what r equals 4 is going to turn out to be, but what about theta equals 10? Let's think about what that has to be as well. So let's think through this. Now, the reason these are interesting is because it gives us these grid lines in our polar form. So obviously, r equals 4 in our polar form, that's going to be a circle of radius 4. We kind of already figured that one out. But if I say theta equals 10, what does that mean? Well, theta equals 10. Oh, it doesn't give me a polar form. I apologize for this. Let me go a different way. Theta equals 10. That means the angle always has to be equal to 10. Now 10, talking about situations here, 10 is about 3.18 in terms pi. So 10 is like 3.18 pi. 3.18 pi. Excuse me. And so that's like a line going through the origin, meaning we're always at this particular angle. We're always at that theta equals 10. We're always at this angle. If I had theta equals pi over 2, it would be what we used to call the y-axis in rectangular form. That's called the line theta equals pi over 2. Theta equals pi over 6, well, that would be the line going through the origin at an angle of pi over 6. And it would go both directions, both out to the right and out to the left. Theta equals pi over 3, again, it'd go out, up to the right, down to the left. So that's the idea. Now, in terms of actually doing the conversions, well, if I say, excuse me, I have to erase that last one. If I have r equals 4, how am I going to convert that to x's and y's? Well, the easy way is to use this part of the equation. So what we're going to do is we're going to square both sides, and we're going to square this. We're going to get r squared equals 16. And then that r squared can be replaced with an x squared plus a y squared. So it's basically just a substitution using one of these things. Now that's a little bit more difficult if we have theta equals 10. If I have theta equals 10, well, the only thing I can really do is take a tangent of both sides. So if I take tangent, let's go ahead and do that. So tangent of theta, whoops, equals tangent of 10. Well, now I can replace the tangent theta with y over x. And I can replace tangent 10 with whatever numerical value that has. And as long as your calculator is in radians, that numerical value is about 0.6484. Not the greatest of rounding it to 4 decimal places. If you want to go out a slightly different number, then feel free to do that. If you want to use tangent 10, that's fine too. So what you see here is we get y equals 0.6484 times x. So we get a line through the origin with any theta equals some number. No matter what that number is, we can clearly see that tangent of that number is going to give me a real number, and you're going to get y equals a line through the origin. Hopefully that makes sense. So lines through the origin, and circles of particular radius are the things that make up my polar grid. You can see why that is now, why all these lines through the origin are there. Just like when we have x equals a number, and y equals a number, x equals a number on the rectangular grid. Let me write that down. X equals, let's say 3, is a vertical line. And on the y end, y equals 4 is a horizontal line. So notice our grid is a bunch of vertical and horizontal lines. Same thing, r equals 4, circles, theta equals a number, lines through the origin. So our grid is a bunch of lines through the origin and circles because of that. All right. Now, obviously, the replacement of gets a little bit trickier as we get more and more complicated, but I want you to practice this. So I want you to take example 4b here, r equals 7 secant theta. Try to rewrite that and end up replacing stuff until you get something that can be converted into a rectangular equation. Go ahead and push pause on the video and see if you can do that. All right, so we have these 4 replacement equations. We can replace an r cosine theta with an x. We can replace an r sine theta with a y. We can replace an r squared with an x squared plus y squared. We can replace a tangent theta with y over x. Now, in this case, unlike the last case, we don't want to square things. So when we dealt with our circle before, we just had r by itself. So squaring made sense in that case. But in this case, we have r equals 7 times secant theta. What's going to make the most sense in this case is to rewrite secant theta as 1 over cosine theta. So we get r equals 7 divided by cosine theta. Then, if I am willing to multiply both sides by cosine theta, I end up with an r cosine theta equals 7. And I can simply replace the r cosine theta with the letter x, right? R cosine theta replaces with the letter x. So that's what you're trying to do in most cases with these polar equations. You're trying to either get an r by itself so you can square it, or you're trying to, maybe multiply by r. So r squareds, r cosine thetas, r sine thetas are really nice to deal with. And so we're trying to make something either have an r cosine theta or an r sine theta or an r squared in it. So that's the idea. Notice that again, x equals 7, that's a vertical line when you graph that in either case. And that vertical line, r equals 7 times secant theta. So that's how you get vertical lines in polar form. I want you to try another one of those. I want you to manipulate this one. R equals 8 sine theta. Go ahead and push pause on the video and do that. In this case, we're going to have to use a different technique. I don't want to square both sides because that sine squared over here is going to give me troubles. I can't divide by sine theta because then I get r divided by sine theta. I want r times sine theta. So in this case, I want r squareds and I want r sine thetas. The easiest way to do that is to take the right-hand side of this equation and the left-hand side of this equation and multiply both sides by r. So what you're going to end up on the left-hand side when you do that is r squared. What you're going to end up with on the right-hand side is 8 times r times sine theta. And now I can replace and do what I want. So I can replace the r squared with an x squared plus y squared. I can replace the 8r sine theta with an 8y. Now, this is clearly going to be some sort of an elliptical shape. I'm not going to go through, completing the squares or anything like that. But you could make this into a standard version of, I believe, an ellipse here. So you can graph that out if you'd like. So I'm going to leave it this way. I'm not going to simplify it any more than what it is right here. Now I want you to try one more. So we've seen a couple of techniques before, or we've seen a couple of techniques. We can square both sides. We can, multiply both sides and get r cosine theta. We can multiply by r, those types of things. I want you to try to convert this polar equation into some sort of a rectangular equation. R equals 12 tangent theta times secant theta. Go ahead and push pause on the video and do that. Okay, so we have R equals 12 tangent theta secant theta. So what we're going to do is start out by replacing the tangent and the secant with their respective sine cosine arguments. So that's because we can go cosine, sine. Now, if we do it this way, I'm not saying this is the only way. If we replace everything with sines and cosines, then here's the technique we would use. We'd say 12 sine theta over cosine theta times cosine, because tangent is sine over cosine, secant is 1 over cosine. Now what I can do is I can get rid of one of these cosine thetas by multiplying both sides by cosine theta. If you do this technique, you get r times cosine theta. Actually, let me show you the step there. So multiplying cosine over here, leaving one of the cosines underneath. So r cosine theta equals 12 sine theta divided by cosine theta. Now, just like multiplying both sides of an equation by the same number doesn't change, multiplying the top and bottom of a fraction by the same number also doesn't change. So you can multiply the top by r and the bottom by r. You'd end up with r cosine theta equals 12 r sine theta divided by r cosine theta, which obviously my r sine theta I can replace with a y, my r cosine theta I can replace with an x, this r cosine theta I can replace with an x. Multiplying both sides by x, you get x squared equals 12y. So that's one strategy you can do. You can break everything down all the way into sines and cosines, and then manipulate until you can get the r's in the right place. Now, another thing you could have noticed is you could have noticed that tangent of theta is actually y over x. And secant of theta, well, I can't do a whole lot with that other than say, well, that's just like 1 over cosine. So what I could have done is taken the secant, 12 secant, 12 over cosine, and then just left the tangent theta as is. So that's another technique if you'd like. Then when I multiplied both sides by cosine, I'd get r cosine theta is equal to, well, 12 tangent theta. Let me, all right. And r cosine theta, we could have replaced with an x. 12 tangent theta, we could have replaced with 12 times y over x. So we could have gotten that and a few fewer steps if we notice the tangent theta can be replaced with y over x. So again, there's not just one pathway to doing a conversion, but again, there's some general techniques that are kind of nice. Manipulating secants and cosecants into their sine and cosine version, um, doing that kind of stuff, thinking about tangent. Sometimes you want to break down tangent into sines and cosines. Other times you just say, well, I already have tangent, so that's y over x. So there's a lot of nice things you can do. So there you go. Algebraic manipulation until you can figure out how to replace things. Now, the next part of the chapter starts or the section, excuse me, the next part of the section starts looking at graphs of polar equations. So we're going to do that in the next video.